Scalar Matrix. Hello everyone. Today, we are going to explore the concept of the scalar matrix. To start off, it is important to understand that a scalar matrix is not a completely separate entity, but rather a specialized form of a diagonal matrix. Now, to fully grasp what a scalar matrix is, we first need to recall our previous knowledge of diagonal matrices. As you may remember, a diagonal matrix is a square matrix, meaning it has an equal number of rows and columns where every single element located outside the main diagonal is 0. A scalar matrix takes this a step further. While a standard diagonal matrix can have any values along its diagonal, a scalar matrix adds one additional requirement. All the elements on that main diagonal must be identical to one another. Over the next few slides, we will move from this general idea to a formal mathematical definition and look at some practical examples to ensure you can identify these matrices with ease. Formal definition. Now that we have a general conceptual understanding of scalar matrices, let us move on to the formal definition to ensure we have a precise mathematical basis. A square matrix B, with elements B sub ij of order n by n, is classified as a scalar matrix if it satisfies the following two conditions. First, the non-diagonal elements must be 0. This means that every element where the row index is not equal to the column index must be 0. Mathematically, we state this as B sub ij equals 0 whenever I is not equal to j. Second, the diagonal elements must be equal. This requires that all elements located on the main diagonal be equal to the same constant value, which we represent as k in mathematical terms. B sub ij equals k whenever I equals j, for some constant k. In simpler terms, you can think of a scalar matrix as a diagonal matrix where all the diagonal entries are identical. With this formal definition in mind, we can now proceed to the next slide, where I will show you a step-by-step process to identify whether any given matrix is a scalar matrix. Step-by-step identification. Now that we have established the formal definition, let us look at how to practically identify a scalar matrix. To determine if a given matrix is a scalar matrix, you should follow these 3 systematic steps. First, we must check the order of the matrix. You need to ensure that it is a square matrix, which simply means the number of rows must be exactly equal to the number of columns. If the matrix is not square, it cannot be a scalar matrix, and you can stop your evaluation there. Once you have confirmed the matrix is square, proceed to step 2. Inspect the non-diagonal elements. You should examine all elements where the row index is not equal to the column index. Every single one of these elements must be 0. If you find any element outside the main diagonal that is not 0, then it is not a scalar matrix. Finally, in step 3, we inspect the diagonal elements. Look specifically at the elements along the main diagonal, starting from the top left corner down to the bottom right. You must check if all of these entries are exactly the same constant value, which we refer to as k. If these diagonal elements differ from one another, the matrix remains a diagonal matrix, but it does not qualify as a scalar matrix. In the next slide, we will apply these 3 steps to a concrete example to see this verification process in action. Illustrative example. Now that we have established the theoretical steps for identification, let us apply them to a concrete example to ensure the concept is clear. Please look at matrix S in this instance. We are dealing with a matrix of order 3 by 3, and we have set our constant, k, to be 7. As you can see in the matrix on the slide, the value 7 occupies the main diagonal, while all other positions are filled with zeros. Let us walk through the verification process step by step, just as we outlined in the previous slide. First, we check the order. By observing the matrix, we can see it has 3 rows and 3 columns. Therefore, it is a square matrix of order 3 by 3, which satisfies our first requirement. Second, we inspect the non-diagonal elements. If we examine the elements in the first row second column, first row third column, second row first column, second and third row, third row first column, and third row second column, we find that every single one of them is 0. This confirms that the condition where the row index is not equal to the column index is fully satisfied. Third, we examine the diagonal elements. Looking at the entries in the first row first column, second row second column, and third row third column, we see that they are all exactly 7. Since all these diagonal elements are equal to our constant k, which is 7, the final condition is met. Because the matrix satisfies all 3 criteria, it is square, its non-diagonal elements are 0, and its diagonal elements are identical, we can conclude that matrix S is indeed a scalar matrix. Now that we know how to identify these matrices, let us move forward to see how this mathematical property is utilized in real-world applications, such as computer graphics. Real-world application: uniform scaling. Now that we have learned how to identify a scalar matrix through the previous examples, let us explore how this mathematical concept is applied in the real world. In fields such as computer graphics and physics, scalar matrices are used to represent a process called uniform scaling. To visualize this, imagine you have a two-dimensional image represented by a set of coordinates. Suppose you want to enlarge this image by a factor of 3 in both the x and y directions, but you want to do so without distorting the shape of the image. To achieve this, you would multiply the coordinate vectors by a scalar matrix, which we will call matrix S in this specific scenario. Matrix S would be a 2 by 2 matrix, where the elements on the main diagonal are both 3, and all other elements are 0. The reason this works is directly related to the definition we discussed earlier. Because the diagonal elements are identical, the object grows equally in all directions. This ensures that the image is scaled up consistently, thereby maintaining its original proportions. Understanding this application helps us see why the equality of the diagonal elements is so important, which will lead us into our next section, where we discuss some common mistakes students make when distinguishing scalar matrices from other types of matrices. Common mistakes. Now that we have covered the definition and seen how scalar matrices are used in real-world scaling, let us discuss some common mistakes students often make so that you can avoid them. First, be careful not to confuse scalar matrices with identity matrices. It is a common misconception that any scalar matrix is an identity matrix. To clarify, remember that an identity matrix is actually a specific type of scalar matrix, where the constant k equals 1. Therefore, while every identity matrix is a scalar matrix, not every scalar matrix is an identity matrix. For example, if you have a diagonal matrix where all the diagonal elements are 5, it is a scalar matrix, but it is not an identity matrix. Second, do not ignore the square matrix requirement. As we emphasized in our step-by-step identification process, a matrix must be square to be classified as a scalar matrix. If you are looking at a matrix with 2 rows and 3 columns, it cannot be a scalar matrix, even if some of the elements are 0 and others are equal. Finally, be cautious not to misidentify a general diagonal matrix as a scalar matrix. Recall from our earlier slides that for a matrix to be scalar, the diagonal elements must be identical. For instance, if you encounter a matrix with 2 and 3 on the main diagonal and zeros everywhere else, it is indeed a diagonal matrix, but it is not a scalar matrix because the diagonal elements, 2 and 3, are not equal. Keep these distinctions in mind as we move toward our final summary of the topic. Key takeaways. First, always remember that a scalar matrix is a specialized type of diagonal matrix. As we emphasized during our step-by-step identification, and when discussing common mistakes, a scalar matrix must be a square matrix. If the number of rows and columns aren't equal, it cannot be a scalar matrix. To confirm if a matrix is scalar, it must satisfy 2 specific conditions. Condition 1, all non-diagonal elements must be 0. Condition 2, all the elements along the main diagonal must be equal to the same constant value, which we refer to as k. Finally, let's look at 2 special cases. If the constant k equals 1, the scalar matrix becomes the identity matrix, denoted by the capital letter I. And if the constant k equals 0, the scalar matrix becomes the zero matrix, denoted by the capital letter O. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of scalar matrices.